This session is going to look at various forecasting methods, and we're going to start with exponential smoothing methods. Smoothing methods are data-driven and are able to adapt to changes in the series over time. In this session, we will explore the weighted average models and exponential splitting, and then compare and contrast simple, mean random walk, and exponential smoothing methods. Weighted averaging is a simple and intuitive method for smoothing a time series and forecasting future values from your past observations. In weighted averaging, weights are applied to past values in such a way to predict the value of the next time point in the series. The values of these weights are selected based upon determination of the importance of these past observations in your data set, which are going to be used to determine the forecast for your future point. So let's start by looking at two very commonly used styles of weighted averages, which are sample mean and random walk. So these are examples where we're going to dive into each of these a little bit further. In this case, what we are trying to do is we're trying to use our past values to predict observation Y9. A common example of a weighted average is the random walk. In this setup, all weights for prior observations are 0, except for the most recent, which receives a weight of 1. In the random walk, where you will be the next time point is only related to the observation immediately preceding it. So as we can see here, we're going to set y hat 9, our prediction for 9. It's going to be fully weighted towards observation number 8. So your immediately prior observation is what's going to dictate your prediction for the next observation. So now let's look at our weighted average example using a simple moving average. In this example, equal weight is placed upon each of the previous observations in the calculation of the prediction for the next time series value. Again, the next time series value we are looking at is y hat 9. So here we are just applying equal weight across all of them. Then we're going to take the sum of the weighted averages, and in this case of our 8 prior observations, to compute our y hat 9. So there is an alternative to where the equal weights do not start at the first observation, as we see here. This alternative will place equal weights to the most recent n number of terms in the series, and then gives each of them an equal weight of 1 over n and 0 to all the remaining prior observations. So if we compare this to random walk, where we're just taking the weights of being equal to 0 for all of them except for the most recent. And then with the simple moving average, we're just picking a window. In this case, the window was 8. And we're going to use a simple average across these 8 observations. And we can just adjust this to omit maybe the first one and look at the prior ones. And so there are adjustments that we can make to this simple moving average. Now, despite the simplicity of simple moving average, there are going to be some disadvantages that we want to consider. One of the disadvantages is that it cannot be used on the first n-1 terms of the series without adding other terms by some other means. Also, because we're looking at a specific window here, if there are extreme outliers within that window, it is going to significantly affect our prediction. It also requires the retaining of the most recent n observations to produce a forecasted value. Also, when using a weighted moving average, it is not a requirement that the weights of the prior n observations be equal. So in this example, the weights can vary across the previous observations in the creation of the forecasted value. Again, we're trying to forecast y hat 9. So here we're using different weights that we can vary across the previous 8 observations. In many weighted moving averages setups where the weights are not equal, more weight is given to the more recent values in the time series and less to the older observations. The premise is that the forecasted value will be more like the observations immediately prior to the current observation and less to those farther in the past. Even including this alteration to the weight, this setup cannot be used until the necessary n number of observations have occurred in the series, unless extrapolation is allowed. If data is missing from a stage within averaging, it can become difficult. sometimes even impossible to reconstruct a changing signal accurately. And so there are some ways to be able to tackle this problem. We're not going to talk about them here, but just know that having missing values in your data could lead to some potential issues in your time series analysis. And lastly, like the simple moving average, the weight of the moving average requires the retaining of the most recent observations to generate your forecast. Exponential smoothing models, or ESMs, was first suggested by Robert Goodall Brown in 1956 and added to by Charles C. Holt in 1957, primarily for the creation of forecasting models for inventory control systems. Exponential smoothing models formulate forecasts using a smoothing method of weighted averages. In the construction of the forecast, more recent observations are given more weight than the observations in the most distant past. The term exponential is derived from the fact that weights not only diminish over time, but they do so exponentially. And so again, the weights emphasize the most recent data, and forecasting, in this case, would only require a few parameters, which is one of the benefits of using this approach. And forecast equations are not going to be simple and easy, they are going to be simple and easy to implement. Now let's look at the forecast equation and see how exponential smoothing works. So here's how we have our formula. So again, it depends on the settings that we use, but effectively the more we go into the past, you can see that we're actually lowering the weights to our class in an exponential fashion. And in doing so, we are applying more weight to the more recent observations and less weight to our older observations. So this is an example of different weights. If we have a weight of 0.5 versus a weight of 0.25, and what those weights would look like when you're looking at the past 8 observations. We can see that the parameter increases. We see an emphasis on the more recent value is also increasing. Now here we have an example with exponential smoothing for seasonal data. We'll talk more about seasonality, but just know that what it does is the weight decays with respect to the seasonal factor. And so there is a way to incorporate seasonality within our exponential smoothing. And what I mean by that is perhaps there are more differences by quarter or by month than what we're able to incorporate into how we implement this exponential smoothing approach. So when should you use the different types of exponential smoothing models? If your time series has a trend, you could use simple exponential smoothing, double exponential smoothing, which is called Brown exponential smoothing, linear exponential smoothing, also known as Holt exponential smoothing, or dampened trend exponential smoothing. So these are all different ways of applying these different types of models. For models with time series that have seasonality, you can use a seasonal exponential smoothing. Models for time series with trend and seasonality can use Winter's additive exponential smoothing or Winter's multiplicative exponential smoothing. But because there are exactly 7 models, trial and error becomes an effective strategy for model selection in the age of our high-speed computers. One of the benefits of using JMP and other computer packages is that the computers are very effective at examining all the different types of models. So we can let our computer choose which model seems to fit our time series data more effectively. And so we will see that when we explore in class that we can, just let JMP evaluate the different types of models that we can apply and then, determine our optimal solution after that.